Right, let's look at chemical analysis. This chapter is very different if you are doing combined and compared to triple, so make sure you know which sections to review and which sections to miss out. So I'm going to start with combined. There's three sections to combined, which both combined and triple need to know, and then I'll move on to triple, but I'll make that quite clear on what is required. Now, there's three parts to the chemical analysis for combined. You've got looking at purity and formulation, chromatography, and also testing for gases. Right, let's start with just looking at purity. Now, purity is the definition of purity you need to know. So it's a substance, so a pure substance is made up of just one substance. Okay, I know it sounds a bit weird, but it's basically a substance that only contains that substance that you're looking at. Now, this could be an element or a compound, so it could be either, and it could be considered as a pure substance. Now, the easiest way to check for impurities in a substance is to check melting and boiling point. Now, we know that pure substances have got a very specific melting point. So if it's a pure substance, they've got a very specific melting point and boiling point. So it doesn't really matter what we're talking about, so specific. And we know that impure substance will contain a range of melting or boiling point. So it will be quite a big range. Okay, so it's a range of melting and boiling point. Now, what you need to just be aware of is that the bigger the range, the more impure the substance is. If you've got a very specific melting or boiling point, then that means the substance is relatively pure. Just one more thing, which isn't always that obvious. One of the things that happens with impurity is if you've got an impure substance, it usually lowers melting point, but it will raise boiling point. So there might be a question on that, which is a bit beyond, I think I would say not beyond, but a bit on the top end of grades. So that's the main difference in what happens to melting and boiling point in an impure substance. Now, formulation, again, should I put that in green? Formulation, again, very specific definition. It's a mixture, so a mixture that has been designed for a specific reason. Okay, so it's got a very specific function. Now, the most obvious formulation that we often use is medication in the form of drugs. So paracetamol, these are formulations that have got a very specific role to play. Other things which are a bit different, but paint is got a very specific role. If paint hasn't got a particular substance that binds the paint onto the wall, then it wouldn't work. But then you've got a massive range of different things, cleaning products, you've got cosmetics, so these are all formulations. They've got basically substances that have got a very specific role to carry out, and that's basically what the formulation means. Formulation. Okay. Now, we then move on to looking at chromatography. Now, with regards to chromatography, I'm not going to go into too much detail of the practical itself. The only thing I would say, the common questions that come up with the practical aspect of chromatography is mistakes. So usually they ask you to identify the mistake, and maybe often they want you to say what the problem it will cause. So the problem caused. Um, so often the mistake is the line. If the line isn't drawn, um, not drawn with a pencil, so often if it's drawn with a felt tip pen, then that causes a problem. Now the problem that it will cause is it will the pen that you will use for the line will dissolve into the solvent. So that's not something you want, and it will also mix with the pigment that you are testing. So that's the problem that it will cause. Okay, so the ink will dissolve into the solvent. Now the other mistake is the water level. So if the water level is too high, if it goes over the base, then so water level over the baseline, then that also can cause a problem, because what will happen is all the pigments will mix and dissolve into the solvent. So the pigment into the solvent. So that's the most common question that they tend to ask regarding the practical. So I'll just leave it at that and I won't go into the details of the practical. Now, a couple of other things, the RF value. So the RF value, you just need to make sure that you know which way round it is. You've obviously got how far the substance moves divided by how far the solvent line moves. If your answer is more than 1, then you have done it the wrong way around. So it needs to always be less than 1 for it to be correct. So you actually measure it out. Make sure you do it from the center of the spot, and that will be the substance, and then how far the baseline, the solvent, they call it the solvent front, how far that goes up the paper. It will always be less than 1. So just make sure that that's the right way around. Okay, so always less than 1. Now, a couple of other things. The 2 phases. You've got the stationary phase and the mobile phase. Now, this is when it starts to move into a bit more of a difficult words, difficult understanding. Now, first of all, you need to be able to identify the phase. So what is the mobile phase and what is the stationary phase? Now the stationary phase is the phase that doesn't move. Most of the time that is the paper, the chromatography paper, and the mobile phase is usually the solvent, so often that is the water itself. So the water basically carries the pigment up the paper. Now, if the pigment is very soluble in water, what will happen is it will travel up the paper the most. And what that means is you need to then discuss it based on its affinity towards the stationary phase compared to the mobile phase. So if the pigment moves up the paper the most, that means it's more attracted to the mobile phase compared to the stationary phase. And if the pigment doesn't move up the paper that much, that means it's more attracted to the stationary phase compared to the mobile phase. So that's the difference in attraction that you need to talk about with regards to how far the pigment will move up. If the pigment doesn't move up at all, that means that the pigment is insoluble. So if no movement, pigment is insoluble. Now, a remedy for that is you find a solvent that the pigment dissolves in, and then it will move up. the paper, so you need to change the solvent in that sense. So that's the chromatography section. Now the last part for the combined is looking at the testing of gases. Now this is relatively straightforward. Now the one that students miss out a lot on is chlorine, so I'm going to start with chlorine. We need to also look at how hydrogen is tested, oxygen, and the one that most students find relatively straightforward is carbon dioxide. Okay, now chlorine is the one that, like I said, a lot of students struggle to remember. The main way you test for chlorine is you get a damp litmus paper. So litmus, or which needs to be blue, so damp blue litmus paper, and what will happen to that, it will actually turn bleach white. So what you end up doing is you end up bleaching it. So that's what happens with chlorine gas. So it's an easy test. You get blue damp litmus paper, and then it will bleach, it will turn white. Hydrogen's a really straightforward one that you've come across a number of times. So you get a burning splint, which goes pop. So it's basically the squeaky pop test, so aka squeaky pop test. Okay, so that's an easy one. It happens because hydrogen is flammable. The oxygen one, with oxygen you just need to get a glowing splint, so it will relight a glowing splint. So not a burning splint, but a glowing splint. You basically burn it, take the fire out, and then what it will do is it will relight that fire. And then the last one is carbon dioxide, which a lot of people know. It will turn lime water milky. Okay, so that's a relatively straightforward test for carbon dioxide. So chlorine, remember chlorine is Cl2, hydrogen is H2, oxygen is O2, and carbon dioxide is CO2. So those are your chemical tests. And that's it for combined.